Guys, welcome to this video. So in this video I've been planning to make this video for quite some time now, and in this video I would like to discuss very interesting, and if you have not heard of it before, then it's a very, I don't know, maybe disturbing idea, maybe definitely mind-bending idea, intriguing idea, and might even be disturbing. But yeah, it's not like any kind of horror story or anything. It's based on physics, of course. So basically there is something called the past hypothesis, first proposed by Ludwig Boltzmann, who probably pioneered the development of statistical mechanics. And based on the past hypothesis, there is this absurd sounding claim which is called the Boltzmann brain, which we'll be discussing in this very video. So finally, see, right now I'm in a, I don't know, I'm in a kind of, this is a place you can come here from the, from the Salamander Lake, which is called the Namthing Pokri in local language, Namthing Pokri Lake. This is not Namthing Pokri. The lake is, that side, slightly that side. I came away from here because this place is very quiet and, no tourists. As you can see all around me, you can see both behind me and forward me because I'm recording in dual mode. And it's very peaceful. I don't know if you can hear the sound of the forest. I mean, I don't know, there are some announcements going on in the back. Maybe most likely there is some marriage or something. But otherwise you can see the very sound of the forest. It's, if you are physically present, very quiet and peaceful. Anyway, you can at least see, you can definitely enjoy the view. You see, it's all around me. It's like very much peaceful. I was sitting here for last 10 minutes quietly and reflecting on this, and it was really great. So yeah, I mean, whenever I look at everything around me, yesterday night I was looking at the view from outside the window of my cottage, of my homestay, and it was like, there was this one side of the room is fully glass and you can see the view outside, and it's the hills and valleys, and in the night you can see those little lights, and I don't know if this is very common even among physicists or among thinkers like me who slightly tend towards existentialism or nihilism or whatever you want to call that. But when I looked at all this, the first thing I felt is the universe shouldn't exist. No, of course I'm not a villain, I'm not Joker or something, although I like the character very much, as I've already mentioned in some of my previous videos. But I don't want to blow things up, and I don't want to create an apocalypse. When I say the universe shouldn't exist, I'm not saying that we should destroy the universe. Since the universe is here, what we should do is try to figure out its origins and its ultimate secrets. That's what I'm trying to do as a physics student. That's what we are all, like I always say, we are all seekers of meaning in our life. Every person, no matter what their profession is, what they do, what they don't, is a seeker of meaning. But yeah, not everyone is a seeker of truth. To be a seeker of truth, you have to sometimes accept that no, there may be no meaning at all. And that level of acceptance, it's at least from my experience, it's not very common in ordinary people. Among physicists, among philosophers, or among not just physicists and philosophers, among people who are a little bit intellectually driven, it's common, but it's not very common also when you consider humans in general. But yeah, I felt like no, the universe shouldn't exist because, see, it's not. It might sound like a very disturbing claim, very nihilistic claim, or very negative, pessimistic viewpoint, whatever you call it. But the reason is that the more I study physics and think about the interplay between the fundamental parameters in physics and the way we have developed physics, or not just physics specifically, when you look at the universe, don't you wonder like why all of this? Why? What was the need of creating all of this? Wouldn't it have been better that nothing existed? Because that's what we would expect fundamentally. I don't know if I'm able to communicate this to you, because this is a very deep realization which cannot be communicated in words. That's true. If you don't have this realization right now, you may think like what I'm speaking is nonsense, and maybe it is nonsense from a practical point of view. Even I do admit that. But you see, the reason I'm saying this is that this is a very deep question in philosophy. Why is there something rather than nothing? And I'm not really a big fan of philosophy. I don't think philosophy can solve our problems, and it's more of a meaningless subject. I won't say meaningless subject. It can give intellectual satisfaction, and it can, even in rare cases, it can provide us with very new insights that can progress the development of theoretical knowledge, maybe even theoretical physics, or understanding of the world as a whole. But yeah, on the whole, I don't think philosophy is personally, I don't think it's as important as physics, because philosophical claims or whatever you say, they're not tangible and they're not. But yeah, again, this question, I don't want to relate this question specifically to physics or philosophy or this and that. I think this question lies at the very heart of existence. Why is there something rather than nothing? And the answer is, of course, we don't know. But the point of this video is I want to impress upon you this realization that yeah, there should have been nothing. Of course, we know so very little about the world around us, so we're not in a position to make a claim like this, like there should have been nothing. I mean, who are we? But think about it, just a thought experiment. If you were God, or I mean, if you were something who can do whatever he or she, whatever you want, then would you take the trouble of, creating a big bang or whatever, call it a quantum fluctuation in vacuum? Would you even bother to make a theory like quantum field theory? I mean, of course, you have not made quantum field theory, but would you care to make it possible that there can be a fluctuation in the vacuum that will give rise to all this entire universe, and that will slowly evolve, and complex structures will form, galaxies, stars, and then in one such star, one such planet, we would emerge in all this complex world around us? Would you really take the trouble if you be honest with yourself? My answer would be no. I mean, that's what we would expect fundamentally, right? So this is the question: why is there something rather than nothing? And past hypothesis. Okay, so past hypothesis is a bit technical, because to fully understand it, you need a little bit of knowledge about entropy, second law of thermodynamics, and statistical mechanics is not required to get the qualitative idea, but knowledge of statistical mechanics is, because fundamentally it emerges from one of the basic postulates of statistical mechanics. So I will try to give you a very rough idea. Okay, qualitatively, of course. I mean, there is no whiteboard here, there is no marker pen here. I cannot make you, like, like make you understand quantitatively, write equations or so. In this forest, I'm all alone, and there are some birds and all. So yeah, it's a very good setting for discussing a topic as fundamental as this, as deep as this. Fine. So there's a very fundamental assumption of statistical mechanics which is called ergodic hypothesis or ergodicity. Actually, it's more technically called the past hypothesis, and it's called sorry, it's more technically called, sorry for the interruption, there are some tourists coming, it's called the postulate of equal a priori probabilities. And that's a very, like, deep postulate, because it's based on an assumption, and as I say, it's a postulate, so you cannot prove it, you cannot mathematically derive, like, okay, this is the postulate of equal a priori probabilities. But I mean, you can at least try to understand why the logic works, and that the answer lies in statistical mechanics. So when we try to develop this field called statistical physics, one of the basic starting point is that we divide a system into its microstates and macrostates. So again, I'll not go into the details, but let's say you have a hotel in the sense you have if you have a multi-storied building, say, so, and in each floor you have a particular arrangement of rooms. Suppose in each floor there are 3 rooms or something. So this entire structure of the hotel as a whole is called its macrostate. It's a macroscopic property, you can observe it, kind of. So what is a microstate then? A microstate would be, the exact microscopic configuration. Like, for instance, if I say, like, there are, I don't know, maybe 10 rooms in the hotel, and each room is numbered room 1, room 2, room 3, room, and up to room 10. So let's assume that these rooms are distinguishable microscopically. Microscopically, you can distinguish, okay, this is room 1 and this is room 2. But macroscopically, you cannot distinguish them. There are just 10 rooms, and that's all we know. And suppose there are 9 guests, so there are nine rooms are full and 1 room is empty. This is the macrostate. That's all. 9 rooms are full, 1 room is empty. But now let's think of it in a slightly more deep way. Now when we talk about microstate, if I say that room 1 is empty and the rooms 2 to 10 are full, that is a different microstate than if I say room 2 is empty and room 3 to 10 as well as room 1, they are full. That's a different microstate. But in both these microstates, the macrostate is the same, the macroscopic configuration is the same, and that is 9 rooms are full, 1 room is empty. So the postulate of equal a priori probability says that for a system in a given macrostate, there can be many possible microstates, right? So they say, suppose there are, just for example, there are 10 possible microstates. Like in our example, you can either keep room 1 empty and all the other rooms full, you can keep room 2 empty, you can keep room 3 empty, and so on. So you have basically 10 possible microscopic configurations that will correspond to the macrostate of 9 rooms full and 1 room empty. So postulate of equal a priori probability, or PEAP, it's often called PEEP. So PEEP says that all the possible microstates for a given microstate for a system in equilibrium, they are all equally likely. System is in equilibrium because, of course, the system is not exchanging energy or information with its surroundings. There are 9 guests in the hotel, means there are 9 guests. Nobody's checking out, and nobody's checking in the hotel. At the time when we're studying the system, it's just 9 guests. No, that's why we call it in equilibrium. So this means, according to PEEP, all these 9 microstates are equally likely. It's not like the configuration where room 1 is empty and the other rooms are full is more likely than the configuration where maybe room 3 is empty and the other rooms are full. Because if you make such an assumption, then you will not be able to explain fundamentally why this particular configuration is more likely. See, actually we don't, like I said, it's a postulate. We cannot derive PEEP, but we can at least logically see why we have assumed this, because any other assumption, our common sense says that any other assumption does not make sense. If I say that no, this microstate is more likely than that, in general for a system, if you make these kind of claims, how can you justify which particular microstate will be more likely or less likely? So that's why to start statistical mechanics, we start with the assumption that no, all the microstates are equally likely, all the possible microstates are equally likely. That is PEEP. And PEEP actually stems from something called ergodic hypothesis or ergodicity, which is, now the relation between ergodicity and PEEP is very nuanced. It's often taught as two separate postulates or separate ideas, but they're very related. If a system does not show ergodicity, then PEEP will not hold for that system. PEEP kind of follows from ergodicity, or you can say the PEEP postulate, it implicitly assumes ergodicity, the idea of ergodicity. And let's see why. Ergodic hypothesis says that the time ensemble of a macroscopic parameter of a system is equal to its the time average of a macroscopic parameter of a system is equal to its ensemble average. I know that it makes sense to you if you have not already learned statistical mechanics. That's all technical jargon, but let's break it down. So time average. Let's say you want to measure some macroscopic parameter of a system. Let's say it's temperature. If you have a box of gas, the most common example, you want to measure its temperature. So very important point to note here is that there can be many possible microstates, many different configurations of the gas particles which correspond to the same temperature, same macroscopic property. For instance, all the gas particles are spread out, or all the gas particles are in a corner. But both these configurations might correspond to the same temperature. You may ask why? Because temperature only depends on the average kinetic energy of the gas molecules, nothing else. So yeah, if the average kinetic energy of the gas molecules can be same in both these configurations, if we think about it, just the average kinetic energy. Yeah, when the gases are more compressed or when they're more spread out, the volume, the pressure, all this will change. PV equals nRT if it's an ideal gas. But kinetic energy does not, if it's an ideal gas, then there is no potential energy, and kinetic energy is a total energy. So yeah, we can have these two very different configurations or microstates, but they correspond to the same temperatures, the same macrostate. Now, according to ergodicity, what is the time average? Now, if I have this system of gas and if I make, this is just an hypothetical argument. It's not possible in practice, but yeah. Time average means if I measured this macroscopic property, what we are measuring, suppose for example in our case we have considered the temperature. So I am performing measurements on temperature. I am performing temperature measurements at infinitesimally small intervals of time and for an infinite number of time. Like I will go on till infinity, just a theoretical hypothetical argument. I'll go on measuring the temperature now just in the next instant of time, then again in the next instant of time, and so on and so forth up to infinity. I'll keep on doing this. And then I will take the average of all these values of temperature and I'll get some average, and this is called the time average. Now you may ask me one thing. So if both this configuration correspond to the same temperature, then if I make these measurements, I'll get the same value. So, and suppose if I make 100 measurements and I get the same value and I add them up and divide by 100, I will get the same value. So if the value does not change at all, if the macroscopic parameter does not change at all, since the system is in equilibrium, what is the point of measuring all these values and then taking the average? Because see, just to give a simple example, it might be possible that we are measuring let's say we are interested in measuring the pressure of the system, but maybe the energy of the system is the fixed macrostate. It's possible, like a system is at a fixed energy, but we are interested in measuring the pressure. Like I said, even in the case of temperature, if we for the two different configurations, one the gas is spread out, the one the gas is compressed. If you were actually interested in measuring the pressure, then the pressure would be different in two cases, even though both the cases correspond to the same energy. So if you were measuring the pressure, then depending on the microstate, the pressure would change. So, and over time, the pressure would also change because the gas is changing, the microstate is changing, all the particles are moving about. And if you take the ensemble average, time average and ensemble average means in time average, you consider single system in space, but you take multiple measurements in time, like through time. In ensemble average, you consider a system and just hypothetically you construct a similar system, many copies, infinite number of copies, to be honest, to be more precise. Theoretically, we assume infinite number of copies. All these copies have the same macrostate, same fixed macrostate. Of course, the macrostates can be different. Otherwise, there is no point in taking copies if everything is same. Macrostate is everything is same. And then at a single point in time, you measure this parameter which you're measuring for all these copies. This is called ensemble as a whole. And then you take the average. That's the ensemble average. Again, you may ask, like, actually this example I gave previously, it's more apt here. You may ask, if the macrostate does not change, why do I need to take so many macroscopic copies of the system in space? The answer is that ensemble average, right? So the answer is that, like I said, say the energy is fixed or the temperature is fixed, but you are measuring the pressure. So then if you take many copies in space, many microstates, then for every microstate, the average value will be, the measurement outcome will be different. So you need to take an average, right? So the ergodic hypothesis assumes that this ensemble average is equal to the time average for all systems in equilibrium if you're measuring a particular macroscopic parameter. And this makes sense. Okay, I'm measuring all the possible values, whether I do it by making multiple copies in space, ensemble average, or I do it through multiple measurements in time average. So it sounds obvious. Okay, ergodic hypothesis says that ensemble average is equal to time average. But even this kind of obvious sounding claim, there are very important implications, and this can lead you directly, this can at least intuitively point at the PEEP, postulate of equal priority probabilities. Let's see why. Let's see how. So when we talk about PEEP, PEEP says that all the microstates are equally likely, right? So when we take the ensemble average, essentially, see, you are taking infinite number of copies of the same macrostate but different microstates. And if you take infinite number of copies, then technically all the microstates will be covered, right? And all the microstates will be covered only once, because that's how we define an ensemble. In an ensemble, one microstate is not repeated, because in ensemble means all the possible copies with the same macrostate but different microstates. So one microstate will not be repeated. So that means, and since we're taking infinite copies, the entire ensemble, you have all the microstates. So that means the ensemble average is the average measurement is the average of measurement outcomes for all the microstates of the system. And now you're taking the average, and if you find this average to be equal to the time average, which is the claim made by this ergodic hypothesis, what does that imply? That implies that when you're doing the time measurement, time average, you are not taking the ensemble, but still you're finding the average values to be equal in both the cases. That means, and you are making measurement through time infinitely, like through, that means essentially an object, I mean a system, it goes through all its microstates through time only once. Because if it did not go through, if it went through the same microstate twice, then the time average would not be equal to the ensemble average, because in the ensemble average you have considered a microstate only once, uniquely, each microstate only once. But in the time average, if suppose you're performing measurements through time and you're finding the same microstate more than once, then your average values will not be equal in general. Ergodic assumption will not be valid, but it is valid. I mean, if we assume it's valid, that means that implies that through time a system moves through or access all its possible microstates exactly once, not more than once. That is the point I'm trying to say. So this means if a system evolves through time and it accesses all its microstates exactly only once, that means all its microstates are equally likely. And this is what PEEP says, postulate of equal priority probability. Because if the microstates were not equally likely, then maybe the system would have preferred to visit one microstate more than once, and so on and so forth. You get the argument. But now this leads to the past hypothesis, which is what I said. Like, it's since technically it's possible for a system of gas which is evolving through time, since PEEP says all the microstates are equally likely. So suppose the gas is initially in a spread out configuration. Just let's say that is the initial microstate. It's totally possible. Now, according to PEEP, it's equally likely that we find the gas in a more, compressed configuration, when all the gas particles may be moved together in a corner. So it's possible that a gas system of gas which is spread out all by itself compresses and goes to a corner. Totally possible. You may ask, like, but then entropy is decreasing. How that is possible? We don't. Yes, entropy will decrease. It's not like you may say that when the gas particles come together, then maybe, of course, their volume is decreasing, so the number of available spatial configurations is decreasing, but they might speed up. Their velocities, energy configurations might vary, and that may result in an overall increase in entropy. But no, we are talking about ideal gas. There is no potential energy, and ideal gases don't interact. So it doesn't matter the configuration. If the volume is decreasing, that entropy has to decrease, right? Now, if entropy is decreasing, then that's clearly, it's a closed system of gas, not interacting. So a closed system by itself spontaneously transitions from a high entropy state to a low entropy state. This is totally allowed under postulate of equal priority probability, PEEP. But clearly this seems to violate the second law of thermodynamics, that entropy must increase. I mean, entropy cannot decrease in a closed system. It either has to increase or remain the same. So all this sounds counterintuitive. But yeah, here's the point. The second law of thermodynamics, it's a very valid law, and yeah, for all practical purposes, we have never found a violation of this law, and we never expect to find one. It's a very useful, very practical. In practical cases, it's a very fundamental law actually. But at the end of the day, it remains a statistical law. The statistical mechanical definition of entropy, it's all based on this kind of assumptions. It's a statistical law. So yeah, while in our universe, I mean, in time scales we are comfortable with, like maybe millions of years, billions of years, for as long as the universe, I mean, usually we don't observe this behavior that a system spontaneously fluctuates to a low entropy state from a high entropy state, or let's put it in other words, to a less likely configuration from a more likely configuration, because more entropy means more likely. Entropy, thermodynamic probability, right? I'm not going into that here. So it sounds very kind of crazy, I know that, but here's the point. if we, at least theoretically, based on these assumptions, this hypothesis, and all of statistical physics is based on this PEEP. PEEP is not just a theoretical, just a figment of imagination. And statistical mechanics makes valid assumptions. You can't ignore PEEP. It's a valid postulate of a theory. If you accept a theory, if a theory makes successful predictions, you have to accept its postulates. So PEEP says that, no, at least in theory, it's possible that fluctuations from high entropy to low entropy state. Now, in our universe, we find that the entropy is increasing, and that means overall entropy of the universe is increasing, and usually things around us get more disordered from ordered configuration. Entropy is increasing. So this is Boltzmann's past hypothesis. Boltzmann says that to explain that why in our universe a fluctuation from a low entropy to high entropy configuration is much more likely than the opposite, than the reverse. To explain this, he assumed that in the past our universe began in a very unlikely configuration, because otherwise, according to P, both are equally likely. Collapse of fluctuation from high to low entropy state or from low to high entropy state. But in our universe, we see that clearly from low to high entropy state, that's much more likely. So to explain this, Boltzmann assumed that maybe the universe started in a very unlikely configuration, very low entropy configuration, and then since the universe was already at a very low entropy configuration, then it's more likely for entropy to increase in the universe. This was the basic statement of the past hypothesis, and Boltzmann said that no, we have to accept this as a fact. We cannot explain this because this is a brute fact. This is a kind of, you can say, you have to accept it as it is, because we observe the world around us, and that's all. You cannot hope to understand this in terms of anything more fundamental. This was the past hypothesis, and yeah, this is still a very deep topic, and there is no consensus, there is no widely accepted answer on anything. But yes, a very absurd kind of thought experiment which comes right out of the past hypothesis of Boltzmann is that it's called the Boltzmann brain, which is what we'll discuss right now before we end up with this video. So it's obvious, if we go by the Big Bang theory, which matches some observations, which is in agreement with observations from cosmic microwave background and many more, then the early universe was probably at a low entropy configuration. The early universe was very smooth. We know from cosmic microwave background radiations, except very tiny thermal fluctuations in the temperature of the kind of background. It's the leftover radiation from the Big Bang, kind of. We know for sure that the early universe was very smooth, and this is kind of surprising because a very smooth configuration means low entropy configuration. There are only few possible ways you can achieve that configuration. If it's a very rough configuration, many irregularities, okay, there is some more complexity, more entropy. So Big Bang was a very tiny point in space with very high energy, infinitely high density, but it was very smooth as far as we know, and that's why it's a very good configuration. I mean, very unlikely and very low entropy configuration, because see, at the early universe, since it was very small in volume, the gravitational pull was very strong, and if there was even slight irregularities, the system would collapse under gravity. But the system was expanded. This is possible only if it was perfectly smooth. Now, this is the past hypothesis, and what's the Boltzmann brain basically? So Boltzmann is saying, okay, so now let's assume that. So we saw that it's possible. A fluctuation, a statistical fluctuation from a high entropy state or from a very likely state to a less likely state is absolutely possible. Though we don't observe it in the world around us as often, but it's possible. So the past hypothesis, the Boltzmann brain says that, see, let me give you two scenarios. Which is more likely? Scenario one is, initially the universe was at a very unlikely state, very high entropy configuration. Very likely state, very high entropy configuration. Then it suddenly, due to statistical fluctuations, it collapses to a low entropy state, to a very unlikely configuration. Like, suppose this is my y-axis, this is my entropy graph, and this is my time, entropy versus time. So initially it was high entropy, then it collapses to a low entropy point, and that was our starting point, Big Bang. We started in a very low entropy, very unlikely state. So which is more likely for this the initially high entropy configuration? Maybe all the particles are arranged or spread throughout and maybe interacting in complex ways, high entropy. Which is it more likely for this configuration, these particles, all of them to collapse in a single point in a Big Bang and then start expanding, and then exactly in the right ways, all these things, particles to form particles, and then particle radiation decoupling, all the four forces, spontaneous symmetry breaking, formation of galaxies, stars, solar system, Earth, then in Earth formation of life forms, all this complex world around us, trees, humans and all. Is it more likely? That it's possible, surely. From a likely state to unlikely state, such a fluctuation, it's possible for these kind of things, you need to wait almost an infinite amount of time. But if you wait an infinite amount of time, according to the ergodic hypothesis, according to PEEP, it is possible that all the particles in a very high entropy universe suddenly collapse at a point, and that's what we call the Big Bang, and then it starts expanding and gradually gives rise to the world around us. Possible. But let's consider scenario 2. Suppose only a few particles from this initially high entropy universe, only a few particles collapse to this is what we call a Boltzmann brain. They collapse to form a single brain floating in space. Nothing else is there, just this brain. collapse to a, when I say the particles collapse to a brain, what I mean is that just by themselves, just to satisfy all the possibilities, just to access all the microstates, these particles, they assemble themselves in such a way that a brain is formed, and this is called a Boltzmann brain, just a brain in empty space. No body, no arms, no legs, no consciousness, just a brain. And this brain is just floating in empty space, but the particles assemble in such a way that this brain is able to form thoughts and, conscious. The brain is conscious, essentially. And this brain has formed this false memory of this entire world around us, this world around me, even my body, this shirt I'm wearing. None of this is true. I'm just a lonely brain floating in deep space, and I'm just imagining all of these things, because that way you can explain the world around me, everything, as just a figment of imagination within my brain. But it's more likely than the initial than the possibility of this entire universe, physical world, actually coming out from this. That is a very unlikely configuration. All the particles have to collapse to a big bang and do all of this. But so why collapse an entire universe? Why not create a single Boltzmann brain and just say that everything else is an imagination of the brain? The brain has imagined the past, but the past never occurred. This is statistically more likely based on whatever we have discussed so far. This seems statistic, and from a purely statistical point of view, yeah, the Boltzmann brain hypothesis or argument makes some sense. It's statistically much more likely that, yeah, it's just a single brain. But this idea is pretty disturbing. Oh my god, nothing exists, I'm a single brain. What are we even talking about? But yeah, there are some problems with this argument, and most physicists believe that no, this is not actually true, even though it's a very good thought experiment which did a very good job about, pointing out some very fundamental flaws, or you can say loopholes, or our limitations in our understanding about these topics. But for one, if this entire world around me was indeed the result of a random fluctuations are random, statistical fluctuations. If this entire world around me was just the result of some random fluctuation, then there would be no regularity in the world. Maybe I perform an experiment now, and I perform the same experiment under the same external conditions. After 2 days, I would expect I might get different results, because it's just a random fluctuation. The world is a result of fluctuation. So even my brain, if I am actually a Boltzmann brain, even my brain can fluctuate, and I can form, even my memories may not match. Like maybe today I'm thinking, okay, 2 days ago I was there, but after some time I might form a different memory. But it's all a random fluctuation. But that doesn't usually happen, except in cases of psychological patients or neurological patients. It doesn't happen, right? And not just memories, it's even like in science, we have formed some laws about physics and science based on our immediately observing, based on observations on the immediate world around us. Newton, for an example, I don't know if this is actually true, but Newton is supposedly said to have developed his law of gravity just by looking at an apple falling. But this same law is he applied to even the earth and the sun and all celestial bodies, in fact. And this law worked for everything. And based on these laws, we make rockets and so on and so forth. See, the point is, we don't even among all these, there is some order and regularity in the world. The laws of physics that we've discovered, at least some of them, most of them in fact, they hold everywhere and every time. It's not like the laws of physics change with time. We have got no such indication. So if the world did not exist physically and was just the result of a mere statistical fluctuation, then this would not be the case. This argument was put forward, most famously popularized by Richard Feynman, okay, who found this idea of Boltzmann brain absurd. Yeah, it is absurd. One more kind of counter argument was recently put forward by Statistical. So according to Statistical, he said that Statistical is actually a very very good, is doing some very good work in these fields, and you can check out he's a professor of physics at Caltech. I even had the chance to converse with him over email once. Not a very long conversation or anything, but he's a very good guy, and I really read his books. My personal favorite is The Big Picture. He has written a book called The Big Picture. Those are all popular science books. He's also written some textbooks, some very good textbooks. I think one is on general relativity, which I have not read personally, but yeah, it's very good. Anyway, so Statistical says that he argues against the Boltzmann brain hypothesis that, look, if indeed we were nothing existed, it was just a Boltzmann brain hanging in deep space, then see, we have formed this idea. Even the idea of Boltzmann brain, this was proposed by Boltzmann based on studying statistical mechanics and studying physics, studying the world around us. So we have studied the world around us and made some theories based on our observations, experiments, and if based on these assumptions, based on these theories, if we are we are arriving at this conclusion of a Boltzmann brain, that it's an entirely random fluctuation. But then Carroll's point is, if indeed the world is just a random statistical fluctuation, then can these conclusions that we have formed on observing the world, on studying the world, can this conclusion be trusted? In Carroll's technical in paper, you can find the paper on archive. Why Boltzmann brains are bad. That's the title of the paper. Why Boltzmann brains are bad. There he technically uses the term cognitively unstable, cognitively unstable, something like that, cognitively random or something like that. Basically, Carroll is arguing that if indeed the world was a Boltzmann brain, then essentially we have arrived at our theories, we have reached these conclusions using this Boltzmann brain, which is according to this hypothesis, which is just a random statistical fluctuation. If that is indeed the case, then this brain would be cognitively unstable. We cannot trust the conclusions that this brain is telling us. So if we assume Boltzmann brain is true, then we are kind of saying indirectly that no, we cannot trust this conclusion. That means it's a kind of contradiction. And according to Carroll, this shows why this hypothesis, although it's no doubt a very intriguing hypothesis, why it cannot be true in reality. So yeah, but yeah, the point of this video, I think I'll stop here. It's already 30 minutes and I have to, go now. I'm in holiday. I'm on holidays and I'm in Sitong. I'm just out sightseeing, and I'm in the name of sightseeing, I've come to a lonely corner of this forest, and I don't know, I'm just recording videos. So anyway, yeah, I don't know, this kind of view, this kind of ambience, this kind of environment, and I won't get this back home, right? So that's the excuse. That's my excuse I give time and again when people say, come on, Arpan, why do you record physics videos? When you go on trips, when you go on travels, you just enjoy the nature. Come on, I'm talking about nature. So that's the point. That was what I wanted to discuss in this video, guys. And yeah, maybe this video was not very coherent because I'm not in my room. I'm sitting in my room in the AC and very comfortably discussing these topics. There is no disturbance. No, it's like tourists can come along any moment. So anyway, see here some beautiful, I don't know what, blueberries or something, I'm not sure. You can see these flowers here. So these are, I think these are, yeah, I'm pretty sure these are cinchona trees, which are medicinal plants used in the malaria and all. So like I said, there's a very good biodiversity in this place. It's a Sitong. It's a small village in the Darjeeling district of West Bengal. It's a hill station kind of an offbeat destination. It's pretty popular right now. As far as I can see, there are a lot of tourists and all. But yeah, anyway. So the point of this video was to, it's really good to think about this Boltzmann brain, past hypothesis, and consciousness. What is even consciousness? And it's so this is actually this reminds. See those? You can listen to the birds. So this talking about the Boltzmann brain, this is all based on physics, statistical physics. But this actually kind of brings the concept of consciousness here. Because to actually understand whether it's possible, you also need to probably to have a good understanding of consciousness. So that is the beauty, like consciousness. This age-old conventional view that no, consciousness is something that should be studied by biologists and physicists should just be studying uninteresting objects like maybe balls and rockets. No, physics is all around the biological physics, complex systems. These are all around the world. These are all everywhere around us. You can see a beautiful view of the mountains there. This is just a little bit higher. I'm just standing on a rock, if you can see, and from here you can get this pretty good view. You see, I'm just anyway, you can just get the view. So point is, yeah, physics is about everything from dull and uninteresting objects like a billiard ball or whatever to interesting objects like even consciousness or complex biological systems, all these patterns forming in nature around us, everything. I really like this place as well. So yeah, I think that's all I want to discuss in this video, guys. Let's not make it any longer until a bunch of tourists comes and destroys the entire ambience. I'm actually pretty grateful that I was able to record this entire over 30 minutes video without any major disturbance. Okay, thank you so much, guys, for watching.